Hello everyone, thank you for being here. My name is Zhihong and I'm a PhD student at UC Berkeley, advised by Professor Sylvia Ratnasamy and Professor Shenker. Today I'm excited to tell you about our work, LOCA, a Location-Oblivious Cellular Architecture. This is the joint work with my colleagues Silvery, Natacha, Shaddi, Christian, Sylvia, and Scott. In this work, we focus on the lack of location privacy in cellular networks. Specifically, today's cellular networks operator can easily profile a user's location information. When a user connects to the network operator automatically knows her location based on the location of cell towers. Moreover, the network operator also knows the user's identity. As a result, the network operator knows both the user's location and the identity. This allows it to easily profile a user's current and past location information, and it's a serious threat to user's location privacy. Therefore, a natural question is, can we protect users' location privacy from network operators? A recent work called Pretty Good Phone Privacy, PGPP, has studied this problem. Given that it's challenging to hide users' location from the network, their approach is based on hiding users' identity from the network. Specifically, the user now attached to the network anonymously, so that nobody knows her identity. This approach does protect users' location privacy from the network operator. However, it suffers from a serious drawback, which is that it makes it hard for the network to provide identity-based services. Identity-based services are services whose correct execution depend on user's identity, such as postpay, QoS and service classes, lawful intercept, and so on. In this example, Alice attached to the network anonymously, which then prevents the network from providing her with customized services. Identity-based services are essential parts of today's network, both in terms of satisfying users' demands and meeting legal requirements. Therefore, it's unlikely that network operators can or are willing to give up identity-based services for the sake of better location privacy. Therefore, in this work, we ask this question: can we provide both location privacy and identity-based services? This turned out to be highly challenging. Fundamentally speaking, the network as a whole needs to know both user's identity and location. It needs to know user's identity for identity-based services, and it knows user location simply because user attached to cell towers. However, if one has access to both information, user's location privacy is violated. So are we doomed here? To our delight, we see a way forward via mobile virtual network operator, MVNO, which at a high level allow us to split the network. To see this, let me briefly introduce MVNO-based architectures. In this diagram, what we show here is actually the traditional MVNO model, where the operator is responsible for both user management and infrastructure operations. With MVNO-based architecture, what happened here at a high level is that the network is now split into two parties, with the MVNO, which we'll refer to as a broker in this talk, like Google Fi, being responsible for user management tasks like authentication, billing, and customer services. The broker then contracts with multiple operators for infrastructure operations. With MVNO-based architecture, users sign up with the broker and receive connectivity from the underlying operators. This emerging MVNO-based architecture turned out to be a great opportunity to provide both location privacy and identity-based services. Specifically, we propose a new approach that is based on strategically hiding different information from the broker and from the operator. The goal is that the broker now knows user's identity, but not her location, whereas the operator knows user's location, but not her identity. This simple approach turned out to be super beneficial. On the one hand, it preserves location privacy, because neither brokers nor operators know both information. On the other hand, this is a natural arrangement that allows broker and operator to collaborate and provide identity-based services. To see this, let's walk through a user attachment in this case. User now essentially encrypts its identity with broker's public key. The operator forwards this message to the broker. The broker can now decrypt the message and therefore know the user's identity. Based on this identity, the broker can tell the operator the set of identity-based services to implement for this user. The operator then enforces this service without knowing the user's identity that it's serving for. To realize this approach, we design and implement LOCA, which stands for Location-Oblivious Cellular Architecture, a novel cellular protocol that for the first time preserves user location privacy while providing identity-based services. Before I talk about the set of challenges LOCA addresses, I will first describe the threat model of LOCA, as well as the incentive for operator and broker to adopt it. In LOCA, we assume semi-honest or honest but curious participants, which means that brokers and operators will follow the protocol and attempt to extract user location information, but they will not perform active attacks. We also assume that broker and operator do not collude, which intuitively is because we need the information split between these two parties. Semi-honest and non-colluding participants is a common assumption for systems like LOCA that focus on preventing inadvertent information leakages. And as I'll describe next, in the paper we'll discuss potential ways to support stronger threat model. We believe that some operator and broker will be incentivized to adopt LOCA, both for financial reason to attract privacy-conscious users and for legal reason to show compliance with privacy regulations like GDPR. As I will describe next, LOCA addressed various challenges and managed to provide provable privacy guarantee under this threat model. LOCA addressed three main challenges. In this slide, I will describe at a high level what these challenges are. These challenges arise from the requirement to implement our new approach. First, our approach needs to hide the user's location from the broker and need to hide the user's identity from the operator. In order to hide user's location from the broker, we need to hide the identity of the operator who served the user from the broker. This is because operators' cell tower deployment is public knowledge and can reveal a user's location information. The emergence of operators with small footprints, such as enterprise and private 5G network, underscore the importance of this requirement. This requirement to hide operators' identity from the broker leads to two important challenges. First, how can a broker verify that the operator is legitimate if he doesn't know the identity of the operator? Second, how can an operator receive payments from the broker if he cannot tell the broker what user is services? In the later slides, I'll describe how LOCA addresses these two challenges in more details. The last challenge that LOCA addresses is to prevent trajectory leakage, which refers to operator inferring user's identity based on her trajectory. LOCA addressed three different mechanisms to address these three challenges. Specifically, LOCA as a protocol consists of 5 phases: registration, attachment, mobility, reporting, and claiming. Due to the time limit, I won't go into detail of the exact protocol, which can be found in the paper. Instead, I will focus on the key mechanisms that allow us to address these challenges, highlight their insights, and briefly describe how they are used in different phases. The 3 key mechanisms are unlinkable tokens, provable aggregate claiming, and user-driven real attachments. I won't go into the last one in today's talk. Next, I'll describe how unlinkable tokens allow us to verify the legitimacy of an anonymous operator. First, let's have an example to have a concrete understanding of the challenge here. When a user attaches, it sends a request. Let's say the operator somehow anonymously forwards to the brokers this request. The broker has no trouble authenticating the user, but he cannot authorize this connection because he doesn't know whether the operator is legitimate or not. To address this challenge, LOCA essentially allows the operator to be pre-authorized but anonymous. Specifically, LOCA uses unlinkable tokens that are blindly signed by operator that allows us to authenticate operators without revealing operators' identity. Moreover, operators communicate with broker via anonymous communication channel, so this IP address is hidden from the broker. This mechanism is used in both registration phase and attachment phase. First, in the registration phase, users sign up with the broker in the same way as today, exchanging information like share secrets and broker's public key. For the operator, it reviews identity and registers with the broker, which allows the broker to authenticate it and verify its legitimacy. After that, the operator will request the broker to blindly sign a token for it. The broker will do so and return a blindly signed token, which we'll refer to as an unlinkable token for this operator, because with the unlinkability property of the blind signature, the broker cannot link the signed token to the original one, and therefore it does not know the identity of the operator who owns an unlinkable tokens. However, the broker can still verify his signature so that it knows that this operator was indeed verified and authenticated in the registration phase. Then, in the attachment phase, operators will use the unlinkable tokens. Specifically, the operator will first broadcast the hash output of his token as its identity to a nearby user. User will then include this information in his message to the broker. After receiving a request, the operator will forward this request to the broker together with its token. Here, the dashed line indicates that the communication happened via anonymous communication channel, so the broker cannot know the operator's identity from its IP address. Now, at this point, besides authenticating a user, the broker can perform two more functions. First, it can verify the token and thus confirm that the operator was indeed authorized before. Second, it can match the hash output in the user's message with the token provided by the operator to confirm that this is indeed the operator the user wants to connect to. After that, the broker confidently authorizes this connection and provide a set of necessary information to the operator, including identity-based services to enforce for the user. After that, operator provides cellular connectivity to the user in the same way as today, which we refer to as session between the operator and the user. As you can see here, in this attachment protocol, the operator doesn't know the user's identity. The broker doesn't know the operator's identity, but is aware of its legitimacy. The latter is because of the use of unlinkable tokens. Now that I have described to you how unlinkable tokens allow us to verify the legitimacy of an anonymous operator, I'll next discuss how provable aggregate claiming allows operators to receive payments without revealing to brokers what user it has services. Again, to understand the challenge, let's walk through an example. When settling payments, user report to the broker about its usage for different sessions. In this case, for the operator to receive payments, the most naive approach is that it reveals identity and it informs the broker about the session it has services. However, this will then reveal to the broker what user this operator has services, and therefore reveal the location of these users, violating the location privacy of these users. So to address this, what LOCA performs is a novel aggregate claiming mechanism. Specifically, instead of directly informing the brokers about what session it has services, the operator will instead report the aggregate usage of its sessions. Aggregate usage is sufficient for the purpose of receiving payments from the brokers. But more importantly, the broker is now obfuscated. Because there can be many, in fact, exponentially many under common conditions, session combination, that add up to the same aggregate value. Therefore, the broker can no longer be sure what user was serviced by this operator based on this claim. We then leverage zero-knowledge proof to make sure that the operator cannot lie about the aggregate usage in its claim. Next, I'll briefly describe how LOCA perform aggregate claiming in reporting and claiming phase. First, in the reporting phase, the operator will have a secret for each of his sessions and anonymously send to the broker hashes of this secret. After that, broker will publish a public session table visible to all operators of all the sessions, including a hash secret for each of his sessions. At this point, the operator who has serviced a session is the only party who owns a corresponding secret that can match with the hash output in the table, which essentially allows it to later prove its ownership of the session. Specifically, in the claiming phase, what happens is that the operator will use its secret and generate a zero-knowledge proof that essentially says, I have secrets for session that add up to X bytes. Because of the zero-knowledge property, this proof reveals nothing about the secrets or the session of the operators. Moreover, the broker can now confidently approve this claim after verifying the zero-knowledge proof. Detail of the zero-knowledge proof setup could be found in the paper. Now that I have shown you how LOCA leverages existing cryptographic primitives like blind signature and zero-knowledge proof, and new primitives like aggregate claiming to address various challenges, I'll briefly discuss the evaluation result of LOCA, which shows that LOCA provides provable privacy guarantee and scale to realistic deployment figures. Specifically, LOCA's evaluation consists of a privacy analysis and a system evaluation. For the privacy analysis, we show that LOCA provides provable privacy guarantee under our threat model. Moreover, while LOCA is vulnerable against attacks from stronger adversaries, its design minimizes the leakages of these attacks. In terms of system evaluations, zero-knowledge proof and blind signature show them to be highly scalable enough to support large-scale cellular networks, and anonymous communication added a latency overhead that can be tolerated. We prototyped LOCA based on our prior work Cellbricks, and Cellbricks was built with the open source project Magma, which Shaddi will later present in this section. we would like to shout out to Magma as a great effort that actually facilitates the deployment and development of cellular design. Lastly, we view LOCA as a first step towards privacy-preserving cellular infrastructure with multiple directions for potential improvement. The obvious one being extending the threat model, where we discuss potential ways to go beyond semi-honest and non-colluding participants. To conclude, in this work, we first present a new approach to preserve user location privacy while providing identity-based services by hiding different information from the brokers and operators in an MVNO-based architecture. We then design and implement a novel cellular protocol, LOCA, that realizes this approach by synthesizing existing cryptographic primitive with new primitive and solve challenges in cellular context. Lastly, we extensively evaluate the privacy guarantee and performance of LOCA and discuss directions for future work. With this, I'm ready to wrap up my talk and answer any questions that you may like. Thank you.